In the previous videos, we discussed a number of important thin film processing techniques. We will now finish our discussion with atomic layer deposition and spin coating. In contrast to traditional chemical vapor deposition processes, ALD procedures consist of a sequential alternating pulses of gaseous chemical precursors that react with the substrate. Each individual gas surface reaction step is called a half reaction. During each half reaction, a gas flow is inserted into the chamber long enough to allow the precursor to fully react with the substrate surface. The reaction of the gas with the substrate is a self-limiting process that leaves no more than one monolayer at the surface. Let's take a look at growth of, for instance, aluminum oxide, which is used in certain types of crystalline silicon solar cells. In the first step, a precursor gas like trimethyl aluminum is inserted into the chamber. This is the same type of precursor gas as used for the MOCVD. One of the weakly bound methyl groups is released from the aluminum precursor and reacts with the hydroxide group to form methane. The aluminum precursor is adsorbed on the substrate, forming a bond with the oxygen atom. In this way, a monolayer of aluminum is grown on the substrate. A second layer will not grow in this step, since the aluminum precursors do not react with metal groups, so it's a self-limiting process. In the second step, the chamber is purged with an inert gas like argon or nitrogen. Then, in step 3, oxygen is introduced in the chamber. Molecular oxygen can be used, but in some newer systems, they use an oxygen plasma. The oxygen bonds with the aluminum release the metal groups. In this process, typical reaction products like water, methane, and carbon dioxide are formed. The reaction is again self-limiting, as the oxygen precursor will not react with the oxygen bonded to the substrate. After a monolayer of oxygen is formed, the chamber is again purged and the sequences can be repeated until the desired thickness of aluminum oxide is achieved. The sequential monolayer steps of ALD means that the grown material has a very high uniformity, even for very thin layers. The downside is that the sequential adsorption and purge step make the process rather slow. The final deposition technique we will discuss is spin coating, which is used for the organic semiconductor PV materials. Generally speaking, for a spin coating deposition, a substrate is placed on a rotating platform. A solution containing the target material, also known as the ink, is placed on the substrate. Then the substrate starts to spin, or increases spin rate to over 600 rotations per minute. The centripetal force combined with the surface tension of the solution spreads the ink out evenly over the substrate. During the rotation process, most of the ink flows off the sides of the substrate. Since the target material is usually dissolved in a volatile material, the solvent evaporates during the spin sequence. Eventually, only the target material is left, leaving a thin film with a homogeneous thickness. Besides the volatility of the solvent, the evaporation rate of the material also depends on the flow rate, temperature, and humidity of air passing over the substrate. The process becomes more complicated when depositing nanolayers for organic electronics, where a highly ordered nanoscale structure is very important. At low rotation speeds, the dissolved nanoparticles diffuse towards the edge of the solution, where a highly ordered film is deposited as the solution evaporates. The deposited film has a very poor homogeneity, however, since the film growth at the edge and at the very center of the substrate is minimal. A balance therefore has to be found between the rotational speed and the evaporation rate, such that the deposited material both has a homogeneous thickness and a highly ordered structure on nanoscale. So, in summary, we discussed several deposition techniques used for the deposition of thin film solar cells. During a PECVD, deposition precursor gases are dissociated in a plasma, As a result of a fast switching electrode, a substrate in the plasma undergoes cycles of electron and ion bombardment. The ion bombardment, as well as the diffusion of neutral gas particles in the plasma, lead to the growth of a thin film. PECVD is primarily used for thin film silicon alloys. Sputtering involves the evaporation of a target material through bombardment by heavy ions. Sputtering is primarily used for the deposition of TCOs, but can also be used for metallic layers and chalcocyanide like the CIGS and CZTS. During an evaporation deposition, the target material is evaporated through resistive heating or by electron beam evaporation. This type of deposition is used for the fabrication of metallic layers. Closed space sublimation involves thermal evaporation of a target material and a small temperature gradient between the target and the substrate to achieve film deposition. Closed space sublimation is primarily used for the deposition of cadmium telluride. A chemical bath deposition involves placing the substrate in a solution containing the target materials and is used for the growth of cadmium sulfide layers. Molecular beam epitaxy and metal organic chemical vapor deposition are epitaxial deposition techniques used for the deposition of 3,5 technologies like gallium arsenide. For MBE, pure elements are evaporated in fusion cells and a beam of these elements is then aimed at the substrate. A layer by layer deposition then takes place under high vacuum and high temperature conditions. In reference to MBE, MOCVD is cheaper, has a higher deposition rate and results in lower purity of the deposited alloy. For MOCVD, target atoms are bound to 3 hydrogen atoms or methyl groups and are passed in gaseous form over a heated substrate. The elevated substrate temperature dissociates the precursor gas and a thin film of target material grows on the substrate. Atomic layer deposition involves a series of sequential alternating flows of precursor gases that react with the substrate. ALD produces very uniform layers, even at very small thickness, but can be relatively a slow deposition technique. Finally, we discussed spin coating, which is used for organic PVD. For spin coating, a solution is placed on a rotating substrate, which spreads the solution out evenly over the substrate. The solvent evaporates, resulting in a homogeneous film. This video concludes the section about thin film processing.